Hi, and welcome to lecture number 5 in Advanced Power Plant Design in the spring 2014 semester. I'm Nick Seifert, and in this lecture we're going to be looking at heat exchanger design, and by the end we're going to be looking at getting to how you calculate both the area of the heat exchanger and estimating the pressure drop in a heat exchanger. I just want to point out that real heat exchangers are really complicated, and there's multiple bypass. There could be bypass. There could be in shell and tube heat exchangers. You have flow going around bends. There's U-tube, straight tube heat exchangers. So what I'm pointing out is the real world heat exchangers are extremely complicated, and you probably need to be an expert to actually design one of these. But in this course, we're going to end up simplifying these so that we can actually get at least some estimates on the areas, and then later in the course when we look at economics, we're going to be using relationships between the area of a heat exchanger and its cost to estimate its cost. One thing we can always do is we can always do a first law energy balance, and for a heat exchanger it's quite simple. Once you put your dashed line and you create your control volume, the first law of thermodynamics is easy to state. It's that the summation of the enthalpy entering the heat exchanger is going to be equal to the summation of the enthalpy exiting the heat exchanger. That's the case for an adiabatic when you make the approximation that we will be doing in this course, that the heat exchanger is adiabatic, meaning heat is transferred from the hot side to the cold side, but at no point in time does any of that energy get transferred to the environment. And we're also assuming that these heat exchangers, there's no generation of work, and that they're steady state. So when you make those approximations, you get the equation shown in the bottom left of the slide. So there's two main type of heat exchangers as far as which direction flow goes. You can also have a third type, which will be even more complicated, where the flows are perpendicular. But here we're going to just take two simple cases. One is co-flow, in which the flow is actually going in the same direction. So what happens is, in a co-flow, at the very beginning there's a huge temperature gradient, and by the time you get to the exit, you get to your smallest temperature gradient between the hot and cold side. We will probably never use co-flow heat exchangers in this course, so I'm going to move now on to the counterflow, and we'll be spending a lot more time with the counterflow. In the counterflow, the flows are flowing in opposite direction. So what happens is there is a temperature gradient on one side, and then throughout the heat exchanger there's a temperature gradient. And you can see in the counterflow case, the gradient, the temperature difference between the hot and the cold side stays normally fairly constant. It's very different than the co-flow case, in which there was very large difference between one side and the other side. And when you are trying to minimize exergy destruction, you want to have a small and constant heat exchanger delta T, rather than and that's what you can get in the counterflow case. In the co-flow, you end up having a region where there's a lot of exergy destruction at the front, and then by the time you get to the end, one thing to notice is that the temperature gradient gets small. And here's the key thing, why we typically don't use co-flow, is that in the co-flow, the outlet temperature on the cold side is limited by the outlet temperature on the hot side, which means that you can never get that temperature above the temperature of the outlet of the hot side. Whereas in the counterflow case, you can get your temperature on the outlet of the cold side to be above the temperature of the outlet on the hot side. You're only constrained in that case by the actual temperature on the inlet of the hot side. And that's going to be key This would be particularly the case in something we won't cover, but in solid oxide fuel cells. You may have a temperature difference between the hot and cold side of let's say 50 degrees, right? But the overall temperature increase from the cold inlet to cold outlet may be up to 500 degrees Celsius, and from the say room temperature to 500 degrees C, and that's only going to be possible if you're in a counterflow design. So here's what a general counterflow heat exchanger would look like, right? In which this is the case in which there's a temperature change across the heat exchanger, meaning the driving force changes across the heat exchanger. So we've got the inlet and the outlet, and as I mentioned before, that temperature cold on the outlet can be above the temperature on the outlet of the hot side. And so we're going to use the symbol delta T sub Y is the driving force for heat transfer, and that changes across from Y is equal to 0 to Y is equal to Y. We're here on the x-axis is the distance along the heat exchanger Y, and on the y-axis we're graphing the temperature. So I want to point out that an exergy analysis is fairly easy to do for a heat exchanger, and for a steady state system when there is no heat being transferred to the environment, this can be simple, and assuming steady state, we can calculate the exergy destruction as basically just the summation of the inlet exergies minus the outlet exergies. And so this is what the equation looks like. And I want to point out, just so we can build some intuition, I'm going to actually, we're going to solve for the exergy destruction in a heat exchanger under one simple case, just to help build some intuition on how the exergy destruction depends on some of the variables. So what we're going to do here is we're going to have a couple variables. We're going to have the temperature cold side inlet. Oh, okay, let me step back a second. We're going to solve this under a particular case in which the flow rate on the hot side multiplied by the C sub P on the hot side is equal to the flow rate on the cold side multiplied by the C sub P on the cold side. And under that case, what you get is that the temperature difference between the hot and cold side is a constant across the heat exchanger, and that greatly simplifies the calculations. So that temperature gradient we're calling delta T1, and what we're calling delta T2 is the actual temperature rise from any of the inlet, from the inlet to the outlet, or vice versa on the hot side from the inlet to the outlet. And under this particular case, where n dot times C sub P is equal to a constant, you can find that the exergy destruction, i.e., or the irreversible entropy destruction times the temperature of the environment. Okay, so the sigma dot irreversible is going to be linearly proportional to the n dot, which should make sense, right? More exergy destruction for a larger, when you have more flow. And C sub P, it also increases with C sub P, right? Which means more heat is being transferred. And what I want to point out here is when you solve that equation, you get n dot times C sub P times the logarithm. And inside the logarithm is 1 plus delta T1 times delta T2 divided by the temperature on the cold side inlet multiplied by the temperature on the hot side inlet, which is TC inlet plus delta T1 plus delta T2. So the key thing to note here is that when the temperature on the cold side inlet goes to infinity, what you find is that there's no irreversible entropy generation, which means if you have something really hot transferring to something else that's also fairly hot, then there's no exergy destruction, right? Which would make sense from a Carnot efficiency point of view. If your temperature is 6,000, you're transferring it down to something at 5,000 degrees, there's virtually no exergy destruction. Okay, so that's the easy thing to point out. Next thing to point out is, so let's say the temperature cold on the inlet is closer to room temperature. The exergy destruction increases with delta T1, meaning the greater the driving force, the greater the exergy destruction. And it's also going to increase with delta T2, where delta T2 can be seen as the total amount of energy transferred. So in the case where what's inside the logarithm, the 1 plus term over here, when that term on the right is small, right, a logarithm of 1 plus a small number is close to that small number. So logarithm of the quantity 1 plus x is roughly x. So in that case, what you'd find is that the exergy destruction, sigma dot irreversible times, which is sigma dot irreversible times T naught, would be equal to T naught times n dot times C sub P times delta T2 times delta T1, and divided by temperature cold on the inlet times temperature hot inlet. And so what you can see here is exergy destruction is going to go up. Notice that the amount of heat transferred would be equal to n dot times C sub P times delta T2. Right? So exergy destruction is going to be equal to the amount of heat transferred times the gradient, and then divided by some of the temperatures on the inlet side. So more exergy destruction occurs when there's a greater driving force, when more heat is transferred, and it decreases as you increase the temperature of the entire system, like on the cold side. So that's why I just want to build some intuition here. The main thing I want to get out of this is that the larger the driving force, the more the exergy destruction. Okay, so now we're going to move on to how do we actually estimate the area of a heat exchanger. And then from that, the other question we're going to need is not only area, but we're going to need to know the pressure drop through a heat exchanger. So the area using Fourier's law, we can estimate that the area is going to be equal to the amount of heat transferred divided by the log mean temperature difference, and then we're going to be multiplying that by the quantity 1 over the heat transfer coefficient on the cold side plus the thickness of the metal that is separating the hot side from the cold side divided by the thermal conductivity of that metal plus 1 over the heat transfer coefficient on the hot side. That's H sub H in this case here. So what I want you to imagine is that there are 3 resistors in series, and that, so just like in the electrical resistor case, you've got a voltage, 3 resistors, and then ground. So in this case, ground can be thought of as the temperature on the cold side, the voltage is the temperature on the hot side, and we have 3 resistors. We have the resistance for heat to flow from the temperature in the center of the hot side of the heat exchanger to the wall separating the hot from the cold side. Right? Heat has to transfer from if this is a gas or liquid, it's got to transfer from the center to the wall. It's got to go through the wall, so that's resistor number 2. And then from the wall, it's got to transfer to the cold side gas or liquid. So that's what we have here, is we have 3 resistors in series. So we're basically figuring out that the area is going to increase, of course, as you increase the resistance of each of those resistors. The easy one to think about is the one in the middle, the metal, if it's a metal, like steel, which is used a lot, is steel or aluminum in heat exchangers. As you increase the distance or the thickness of the wall material separating the hot from the cold side, you're going to end up increasing the resistance and hence increasing the area of the heat exchanger. So before we go on to learn more about how we calculate the H sub C and H sub H, I want to point out that I want to give the definition of the log mean temperature difference. And that definition is that the log mean temperature difference is the difference between the hot and cold side at y is equal to 0 minus the temperature difference between the hot and cold side at y is equal to L. So those are the two ends of the heat exchanger. And then we're going to be dividing that by the logarithm of those two differences, the logarithm of the ratio of those two differences. When the differences are equal, you'll notice that this equation looks like it's 0 divided by 0. So you have to use L'Hopital's rule. And what you'll find is that the log mean temperature is just equal to TH minus TC, which is a constant in this case, as you would expect. And so I want to point out a couple assumptions that kind of go into the first equation. These equations are valid if the thermal conductivity is not of the wall or of the material itself, of the gas or liquid, is not a strong function of temperature, and if the specific heat of the fluid is not a function of temperature. These are not true in general, but still this equation is can be fairly safe to use when you're not talking about major increases in temperature across the material. In that case, you might need to do a more realistic model. That, but for using this eventually in cost estimating, this equation is extremely useful, and we'll be using it in this course because of its usefulness. Because if not, you would actually have to integrate along the length of the heat exchanger to figure out the area required. So one of the assumptions I mentioned was that the thermal conductivity is not a strong function of temperature. So what I've graphed here is I want to point out that thermal conductivity is definitely a function of temperature. And I'm graphing here the thermal conductivity of stainless steel. When you're at low temperatures, the conductivity is a huge function of temperature. But once you get to 300 degrees Kelvin, I've shown here 300 degrees Kelvin, the conductivity is about 140 milliwatts per centimeter Kelvin. Whereas when you get out to 500 Kelvin, it's only about 170 milliwatts per centimeter Kelvin. So it is a function of temperature, but you can fairly safely just take the average value, and the equation above will be valid. So take the average. So when you're using conductivity, use the average value between the temperatures on the heat exchanger. I want to give some values that you can use. Point out that aluminum has a very, very high thermal conductivity, which is nice because it means that you can keep down the area of the heat exchangers. It has a value about 250 watts per meter Kelvin. Carbon steels have a decent value of thermal conductivity. If you need steels that can handle maybe fluids that might be caustic, sodium hydroxide in aqueous solutions, you're likely going to need stainless steels or stainless steel 316, and you can see here that their thermal conductivities decrease. And that is a somewhat unfortunate thing, because what it means is that as you make the steel more tolerant to impurities and to caustic materials, its heat transfer coefficient drops, which is one not only also compared to carbon steel, stainless steels are more expensive. So this is one of the things that you have to watch out for when designing power plants, is that you can't just, let's say you design something for carbon steel, and let's say it's kind of a flue gas going to a Rankine cycle, heating up the water on a Rankine cycle. If you just were to swap out into a stainless steel, not only do your costs increase just because of the material, but you also have to look at the fact that your heat transfer coefficient is likely dropped significantly, and that could have a negative effect on the overall power plant. So if you in the equation, there were the heat transfer coefficients, those H's. So what I want to point out here is that H is a function of the Reynolds number of the flow. And when you're in the laminar flow, H has a fairly simple equation, so laminar here being the Reynolds number is less than about 2,000. In that case, the heat transfer coefficient is approximately 4 times the thermal conductivity of the fluid divided by the hydraulic diameter, d sub h. d sub h is the hydraulic diameter, and it's a hydraulic diameter is a ratio of the perimeter and area of a tube. So what we see here is it's a constant times the thermal conductivity divided by the hydraulic diameter. When you get to turbulent flow, so that was for the laminar case, when you get to turbulent flow, which is roughly Reynolds number greater than 5,000, the equation is a lot more complicated. Now H is not only a function of K over D of the hydraulic thermal conductivity of the fluid divided by the hydraulic diameter, is now a function of the Reynolds number and the Prandtl number of the fluid. The Reynolds number is the hydraulic diameter times the velocity divided by the kinematic viscosity. So this can also be put in terms of the dynamic viscosity, and that is such that you have the mass density times the hydraulic diameter times the velocity divided by the dynamic viscosity. So that's the Reynolds number. Low Reynolds number is laminar, high Reynolds numbers is turbulent. I want to point out the Prandtl number is a ratio of the kinematic viscosity to the thermal conductivity. Here, when you put in units that we're more used to, it's the specific heat constant of the fluid times the fluid dynamic viscosity divided by the thermal conductivity. So here's, just want to point this out again. If you take the heat transfer coefficient times the hydraulic diameter and divide it by the thermal conductivity, you have something called the Nusselt number. And so the Nusselt number is equal to roughly 4 when you're in the laminar region, and then you can see it increases, and then once you get into turbulent flow, that's the Nusselt number is now goes like the Reynolds number to the 0.8 power. So this is a graph, and I'm showing the website below where you can access the where this graph comes from. It's from a heat transfer textbook. And the data is actually, in that book is actually from a paper by Krith, and it's using data from air in a heat transfer pipe. So this is actual data from air as looking at the basically the heat transfer coefficient as a function of the Reynolds number. So of course we want to be able to estimate the viscosity of a gas, because we're going to be needing to know that when we design heat exchangers. So there's luckily a fairly simple equation for the viscosity of a gas. It's as opposed to the viscosity of liquids can be extraordinarily complicated. The viscosity of liquids is pretty simple, and So the equation in variable form is that the dynamic viscosity of a gas is equal to the mass density times the velocity times the mean free path of collisions divided by 3. And for gases, you can solve that this is roughly equal to 2.7 times 10 to the minus 6 times the square root of the molar mass of the gas times the temperature. That's all in the square root. And then divided by the cross-sectional area squared times sigma sub mu, sigma sub mu, where sigma sub mu is a cross-sectional integral, or a collision integral, and it's defined at the very bottom here. Big sigma sub mu is roughly equal to half plus 1.1 divided by x to the 0.6, where here x is equal to the actual temperature divided by epsilon. Epsilon here is the Leonard-Jones well depth. We talked before about van der Waals gases, and if you remember in van der Waals gas we had that well depth. Well, here the well depth for Leonard-Jones is very, very similar. Same kind of concept. We have some kind of well depth, and in Leonard-Jones there's also the size, which was size went kind of like that B coefficient, and the depth kind of went like A in a van der Waals gas. So here that well depth is given in units of Kelvin, and it's a depth. It's like an energy depth, and you're basically dividing it by the Boltzmann constant to be able to turn that into an epsilon, into a temperature. And so you can see here that well depth is particularly large for water vapor, and it's really small for hydrogen. Okay, so when you have that, when you have those, when you have that, the well depth E that goes into the sigma sub mu, and the Leonard-Jones size which goes into the collision cross section, you can now calculate the viscosity of a gas. I want to point out the thermal conductivity of a gas is also fairly easy to calculate. Once you have the viscosity, you just multiply it by the quantity C sub P plus 1.25 times R. So I mean, if you know the specific heat constant and you know the viscosity, then you know the thermal conductivity of a gas. And so on the slide before, we said that the Prandtl number looked like C sub P times mu divided by the thermal conductivity. So if there's a relationship, so for gases, since there's a relationship between K, mu, and C sub P, what we find is that the Prandtl number of a gas is equal to 4 times gamma divided by the quantity 9 gamma minus 5. So gamma being the ratio of specific heats, C sub P, which is C sub P divided by C sub V. Once you know that for a gas, then you can very quickly calculate the Prandtl number. And for air, it's a value of about 0.7. So the last thing we're going to be doing in this lecture is looking at the pressure drop. And we're going to be needing to know the pressure drop because if we were to make the heat exchanger larger and larger and larger, we would find that the pressure drop would continue to increase. If we make the length of the heat exchanger longer and longer, we find that the pressure drop would increase. And we have to somehow pay for this pressure drop. Pressure drops, don't come for free. It typically means that you have some compressor you're going to have to run hard, more power, and hence less power from your power plant. So when we get to the optimization part of this course later on, we need to know both the area of the heat exchanger so we can estimate the cost, but we also need to know the delta P because we need to know how much compression we're going to need to supply to overcome that delta P. So let's go through quickly how we'd estimate the pressure drop. So the pressure drop is going to be equal to the friction factor times the length divided by the hydraulic diameter multiplied by the mass density times the velocity squared over 2. So the way to think about this is that pressure drop increases with friction, increases with length, increases with velocity, and is going to decrease as you increase the hydraulic diameter. So there's other ways of writing this equation. You can see here you can put it in terms of the Reynolds number, because maybe you don't know the velocity, but you know the Reynolds number. Or what if the last of these equations, I've put the pressure drop is equal to the friction factor multiplied by the molar mass multiplied by the molar flow velocity in moles per second, that's squared, multiplied by the length, divided by 2 times the molar density times the number of tubes squared times the hydraulic diameter to the 5th. So let's think about this for a second. So as the friction increases, right, we got more of a pressure drop. As we try to put more flow through the system, it's going to go like, the pressure drop's going to go like the flow squared. It's going to also increase with the length, linearly with the length. It's going to be inversely proportional to the molar density. So when you have something that's very, very dense, you're going to be having less pressure drop than for something that is not dense, if you have the same amount of moles per second going through. The other thing I want to point out is the pressure drop goes like the number of tubes to the -2 power. Right? The more tubes you have, the less pressure drop. Now the more tubes you have, it's probably going to be more costly, right? As far as capital costs. So you can see that there's likely going to be some kind of optimal number of tubes, where if you don't have enough tubes, you're going to have a huge pressure drop, and you've got to pay for that in a compressor. But if you have too many tubes, you're going to end up paying for it in capital costs. And the same is true for the hydraulic diameter. You can see here it goes as the inversely it goes as the -5 power. So once again, there's going to be some kind of optimal hydraulic diameter to these tubes. And that's what we'll get into later in this course, is how do we actually solve for what that optimal number of tubes is and diameter of the tubes. Next thing I want to point out is how do the friction factor is defined both in the laminar and turbulent regimes. And in the laminar regime, the friction factor looks like 64 of the Reynolds number. So if you know you're in the laminar regime, it's a really simple equation. If you know you're in the turbulent regime, like greater than 5,000, friction factor looks like 0.2 divided by the Reynolds number to the 0.2 plus about 0.018. And that's if you have a tube whose roughness factor epsilon is equal to 0.001. So I want to point out that equation is only valid when the roughness thickness divided by the diameter of the tube, hydraulic diameter of the tube, is equal to 0.1%. But I use that value because that is a very typical value of epsilon for steel pipes. When you were between 2,000 and 5,000 Reynolds numbers, you need to use some kind of approximation, and you can roughly approximate that the friction factor looks like a combination from the laminar and turbulent regimes. And so that combined equation is roughly valid over the entire span. Of course, when you know you're in the laminar, you should be using just the laminar equation. So what I want to point out here is, so you can solve for the area, but we know that there's a relationship between the area and the length, L. So you can solve for the pressure drop when you solve for the length using the A is equal to Q dot over LMTD equation. Solve for the length and put that into the equation for the pressure drop. And then if you make an approximation to, if you assume some type of isothermal compressor, you can make an approximation to how much work is consumed to overcome that pressure drop. And you now have an equation that shows how the work is going to increase with the flow rate cubed, right? So the more flow you have, you're going to require a lot more work. The delta T, the work required to overcome the pressure drop goes like the delta T increases linearly with the amount of heat that needs to be transferred to heat up the fluid. It's going to go like the number of tubes to the -2 power, right? So the more tubes you have, the less work. It's going to go like the hydraulic diameter to the -4 power. So that means the larger the tubes, the less work you need. It's going to go like the log mean temperature difference inversely. So this is one thing I want to point out here. The amount of work needed to make up for the delta P, basically the frictional loss of work, goes inversely with the log mean temperature difference. So you'd think, well, let's have a log mean temperature difference. But of course, the exergy destruction in the heat exchanger due to heat transfer is going to be linear with the log, roughly linear to the log mean temperature difference. So you can see once again there's going to be some kind of optimal value of the log mean temperature difference, because you can see the overall amount of exergy destruction looks like it's going to have some term divided by log mean temperature difference plus some other constant multiplied by the log mean temperature difference, and basically optimization of x plus 1 over x, you find that there's going to be an optimal value. There's going to be some point, some optimal log mean temperature difference, just as there's going to be some optimal number of tubes and hydraulic diameter. But to really do this, we're going to, of course, need to introduce economics, which we won't be covering for quite a number of lectures. But I just want to hopefully build your intuition about what's going on here with heat exchangers, how we calculate the area, and how we calculate the pressure drop, so we can try to figure out how expensive the heat exchanger is going to be and how much work is going to be required to overcome that pressure difference.